Each of these organic families follow a certain pattern in the way that they are arranged and the way that the carbon atoms bond to other elements. We call that pattern, so to speak, or that family pattern, a homologous series. And that is a group of compounds with the same functional group and the same general formula, right? So an example of an homologous series would be either CnH2n plus 2 or CnH2n or CnH2n minus 2. As you can see, as we go down these patterns from the one down to the other, they have 2 less hydrogens every time. And if you go and inspect all of the alkanes follow this pattern, this general formula of CnH2n plus 2. The alkenes follow this pattern of CnH2n, and the alkynes follow the general formula or homologous series of CnH2n minus 2. You can actually go and taste that for yourself. Let's go and have a look. We can name a few alkanes. So if you look at methane, it's got 1 carbon and 4 hydrogens surrounding that 1 carbon. If you look at the next alkanes, group of alkanes, then we look at 2 carbons on the chain, and that of course would look like this. 2 carbons bonded to each other, and they all have to have 4 bonds around themselves respectively. So at the end of these bonds would sit your hydrogen atoms, right? And of course we can see here that there are 6 hydrogens bonded to 2 carbons. If I look, for example, at pentane, then there are 5 carbons on the chain. And I'm not going to draw the hydrogens in, but we're going to just now assume they sit at the end of these bonds to the carbons. And so you can go and count the number of hydrogens bonded to 5 carbons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we can go and write a general, if we just write the molecular formula for this down, this is 5 carbons, and we said 12 hydrogens, right? That is for pentane. If we look at ethane, there are 2 carbons and 1, 2, 3, 4, 5, 6 hydrogens. This is ethane. There are 2 carbons in the chain, and so the prefix is eth. There's only single bonds between the carbons, and so the suffix is ane. Here there are 5 carbons, so the prefix of the name is pent, for penta meaning 5, and ane because there's only single bonds between the carbons. This, of course, has the molecular formula CH4. As you all know, this is methane, and it's also an alkane. So these all end with the suffix ane because they are all alkanes. And their prefix will be determined by how many carbons there are. We said if there's 1 carbon, the prefix is met. 2 carbons, et. 3 carbons, prop. But, pent, hex, hept, oct, non, and dec. Right? Those are the prefixes to tell you how many carbons are on the chain. And the suffix is going to be determined by what the functional group is, what type of compound that essentially is. These are all alkanes, and so the suffixes would be ane in each case, respectively. Now, if we just look at the pattern that these subscripts in each of these molecular formulas follow, we can spot a pattern, right? So we can say, okay, if there's 1 carbon, there are 4 hydrogens. Maybe what can we do with a 1 to get to 4? You may only multiply first of all and then tweak from there. So you can maybe double it up. If you double up 1, you get 2, but there's 4 hydrogens. So, okay, let's add 2. Let's see if I take that number of carbons and I said I double the number of carbons, and then I add 2, I get the correct formula for methane. Does this formula, this general formula, also apply to and work for this molecular formula? Let's see if N is going to be 2, then what would the number of hydrogens be if it follows this pattern? Well, 2N, meaning N is now 2, so substitute 2 into the place of N, and that gives me what he says. Oh, 6. Oh, right. This also works for ethane. Does it work for pentane? Let's see. If there are 5 carbons, then how many hydrogens will there be bonded to those 5 carbons? Well, 2 times 5, which is 10, plus 2. Oh, right. So that also works. And so you will find that you can now use this general formula. We call this the homologous series, right? You can use that homologous series to now predict the general formula for any number of carbons on an alkane. Say, for example, there are 100 carbons on an alkane chain, then the general formula would be C100H 2N plus 2. So double the 100 and add 2. So that's double 100 is 200 and add 2. So the general formula for that alkane with 100 carbons in the chain and single bonds between them would have 202 hydrogens surrounding it. This is called a homologous series. Now, you can do the same sort of exercise with the alkenes and the alkynes, and you will find that with the alkenes, the general homologous series is CnH2n, and for the alkynes, CnH2n minus 2. As we said, for the alkanes, it is CnH2n plus 2.